Okay, welcome back. This tutorial is on how to implement a full adder using logic gates in the program MMLogic. In this walkthrough, I'm going to show you how to use the program MMLogic, talk to you about what it is, and then we're going to use MMLogic to build a full adder. A full adder is a device that can do binary addition, and it's one of the key components inside a computer. MMLogic is a program that is designed to allow you to diagram and simulate what happens in electrical circuits. This is what the MMLogic interface looks like. This is the canvas where you can draw different types of circuits. This is your palette, which contains all the different devices and tools that you can use. This button here toggles the visibility of the palette. And also there's a pretty good help that you can go to. And if you go through it, it walks you right through states of a node, modes of operation, and how to set up a simulation. There are some tutorials on how to use the different tools. And it's highly recommended that you consult the help if you ever get lost or stuck, or even if you're just curious about what the different items in the palette can do when you're using this tool. Okay, so let's talk about some of the basic things that you have. Now, we talked about Boolean algebra before, and we talked about how computers can represent things in two states, on or off, 0, 1, true or false. In MMLogic, the thing that we use to represent that is called a switch. So I'm going to click on the switch and then come out and click on the palette here. Now I have a switch, and you can see that it's got a 0 and a 1 representing off and on, the two states that it can represent. This is one of the inputs into our system that we're going to build. And so in order to figure out the outputs, we're going to use the LED tool. And so I'm going to click on LED. I'm going to come out onto the desktop, and I'm going to move this over so it's near my switch, and I'm going to connect the two with a wire. Right? So you click on the wire and then come out and hold your crosshairs over one of these little terminals on the input, and then connect it to the terminal on the LED, which which is the equivalent of our output. Now click back on my arrow. Now if I want to see if this works, I can run the simulation. The way you run the simulation is use this play button up here. So if I click play, you can see the grid goes away, and now if I click on my switch, you can see now it's in the on position, my LED comes on. If I click it again, it goes off, my LED goes off, which is what we would expect. Right? So this output mirrors the input. Right? And this is the equivalent of saying in Boolean algebra, A is A. Right? So whatever's in the A column is mirrored in the A column because it's an equivalent thing here. Okay, so let's do something a little bit more tricky than that. I'm going to move this down like this, and I'm going to bring out another LED. And this time I'm going to get the most basic logic gate, which is the inverter, or the NOT gate. And I'm going to drag a NOT gate out here, and I'm going to get a wire, and I'm going to attach the NOT gate, our input here, to the input of the NOT gate, and the output of the NOT gate to our other LED here. Right? And now let's run our simulation again. And now you see that when our input is off, it gets inverted into being on in the output. And that's the same as saying if this were A, then this would be not A. And that's how that would be represented in our Boolean algebra. As you can see that this is still connected directly to the input, so it shows exactly what the input shows. So 0 and off. Right? And if we set that to 1, then you can see that these things change. So when this is on, this is off. So again, A, not A, A, A. Alright. So let's wipe this clean here. you can select it all, hit delete, and then I'm going to start a new one. I'm going to grab two switches this time. Now we want to have two inputs, and we are going to grab the next operation, the logical AND operation. Remember, this is the symbol for AND, and we're going to grab an output so that we have a way to determine what's happening. In fact, let's put a couple more outputs just to use as monitors. Now we're going to grab our wire tool, and we're going to connect the output from our inputs to the input side of our AND gate, and then connect this to our LED. And I'm also going to connect these here like this, just so we can monitor that these are really coming on. Okay, just a little bit of insurance. Okay, so here we're running our simulation, and we see if we turn on input A, right, that it's definitely coming on, but our output from our AND gate is not come on, right? And if we turn on, so let's turn that off. Now if we turn on input B, we can see that it definitely comes on, but again, our AND gate does not come on. Now if we turn them on both together, now we can see that this comes on. If you remember what the logical AND condition was, it was AND means that both of the inputs have to be true. So if this is on and this is on, and this is on, then our output from our AND gate will also come on or be true. Okay, so we can see how the logic of the Boolean algebra that we talked about in the last one gets implemented in these gates. Now, let's get rid of this and this just to simplify our interface a little bit. And let's recall our truth tables that we had before. And we can remember that if we had 0 and 0, that the AND operation of 0 and 0 produces 0. If we had 1 and 0, that the AND operation still produces 0. If we had 0 and 1, the AND operation also produces 0. And finally, if we have 1 and 1, the AND operation produces 1. Okay, so let's stop that, and let's delete this one and swap it for an OR gate. And let's grab our wires and connect them up just like that. Okay, run our simulation. Again, the OR gate, if it's 0 and 0, neither of them is on, and so our output of our OR gate is also off, or right, it's 0. If we set this to 1, then the OR gate says if this one or this one is on, then set the output to on. Right? If we turn that off and this one on, we see the same thing happen. So this one, A or B, if A or B is on, then the output will be on. And in this case, A and B being on also makes the light go on, because it can be one or the other or both in this case, right? Is the way that works. Okay, and the third case then would be the exclusive OR. All right, let's move this one out here. And run our simulation. Now if you see that this one is on and this one is off, then the OR case holds and the light comes on. If we turn this one off and this one on, again the OR case holds and the light comes on. If we turn them both on, the exclusive OR means one or the other, but not both. So that means if you've got one on, that's okay. If you've got the other one on, that's okay. If you've got both of them on, though, then that's not okay, and it turns our output light off. All right. Some things to be aware of in this MMLogic. You can pull up the properties of a gate. Sometimes gates can have 3 or 4 inputs. The other thing you can do is you can invert it. So you can change an XOR, an exclusive OR, into an XNOR, and you can see how the little circle appears here, which indicates that this is the inverse of the XOR gate, right? And so just to show you that that works, we'll run the simulation, and then in this case, the XNOR means if neither of them are on or neither of them are off, then the light should come on. So they're both on, and so the light comes off. They're both off, and the light comes on, right? But if you have a combination of either or being on, but not both, then the light will be off. And this is the inverse of the previous one we looked at, the XOR case. All right, got the basics down? Those are pretty much all of the features you'll need to use. One more I'll show you is the text tool, and we're going to use this to label the parts of our system. So if we were doing this in the Boolean algebra, then we would label this input A and this input B, and then this output would be labeled A XNOR B, and that is in recognition of the type of operation that's put here, and this indicates what happened, right? And then we could create our truth tables by playing with these switches and figuring out what result it has on our light. Okay, so those are all of the basic things you can use. If you want to use any of these other widgets down here, then please feel free in your own time to explore this interface and mess around with it. Alright, so now that we have the basics, let's look at simple binary addition and implement a binary adder in MMLogic. Alright, so here are two binary digits, and we're going to add them together. Right? So 0 plus 1 is 1. If we think about this in terms of our Boolean algebra, then we have input 1, we'll call it A. We'll have input 2, we'll call it B. And then we'll have the output, which we'll call S for sum. So what we want to figure out then is what logic gate should we use to implement this function in our machine? Well, to figure that out, let's create a truth table. And the question is, again, what operation to perform? Well, let's look at our digits. If we were doing a binary addition and we added 0 and 0, like in the first row of our truth table here, the result we would expect would be a 0. If we were to add 0 and 1, as we have actually here on the left, we would expect the result 1. Conversely, if we add 1 and 0, we would also expect a 1. And if we add 1 and 1, then we would get a 0 in the first column of our addition. So looking at this truth table now, with the inputs A and B and the outputs, which read from top to bottom are 0, 1, 1, 0, which logical operation is represented here? If you go back and look at the truth tables for all of the logical gates in the last lecture, you would see that this is an exclusive OR condition. So the way that you implement addition, binary addition, in the simplest form in MMLogic would be to use an XOR gate. So let's go do that. We're going to go back to MMLogic here, and we're going to grab two inputs, and we're going to get an output, and then we decided it was an XOR gate that would be used to implement them. Okay, so let's put an XOR gate in here, and let's grab some labels to make sure that we label everything correctly. And now we'll wire it up. So we need to connect this here, and this here, and this here, and grab our arrow. This is input A, and this is input B, and this is our sum, S. Okay, and so test it out. Alright, so we have 0 plus 0, good, equals 0. 0 plus 1, or 1 plus 0 equals 1, good. 0 plus 1 equals 1, good. And now 1 plus 1, we should get a 0 in this column. Alright, so our adder works so far. But wait, you say, Morgan, what are you doing? What about the carry? And as you probably figured out, 1 and 1 doesn't just equal 0, but it actually should make you carry another digit to the next column. Alright, so let's figure out what we should do with the carry. Now here's a situation where we're adding 1 and 1. And we put a 0 in the sum, and then we have another 1 that gets carried to the next column. I just put some grayed out zeros in here just to remind you that those digits in that column are 0. And again, our sum would then be 10, which is the binary representation for the decimal number 2. Alright, so we have our A and our B as inputs, but this time let's use the number that got carried as our output and figure out what logical gate we might use based on A and B to get that digit that was carried. So here's our truth table. Again, we want to figure out which logical operation we want to use to implement the carry operation. Okay, so if A and B are both 0, 0 plus 0 is 0, right? And you would not expect a carry, so the carry place, S, would be 0. If A is 0 and B is 1, you would also not expect to carry a digit, so this would be 0. If A is 1 and B is 0, again, you're not going to have a carry. You're not going to carry a digit to the next column. The only case in which you're going to carry a digit to the next column is if A and B are both 1. And you should recognize by now that this truth table is corresponding to the AND operation. And so we need an AND gate to represent our carry. So let's go do that. Let's go back to MMLogic and let's grab an AND gate and throw it out here. And I'm going to make it line it up with my thing up here just to be neat. And let's grab a wire and connect one of our inputs to A and one of our inputs to B, and we need to grab an LED and stick it out there, and we'll put it down like so, and grab another wire and connect it, and we'll also label this, and we're going to call it C for carry. So what should happen now is if we did this right, then when we add these digits, if we add 1 and 1, then we'll get a 0 here because for the sum, because the digit that would get entered in the sum under 1 and 1 is 0. But we would also get the light here turning on to indicate that there's a carry that needs to be carried to the next column. So let's run this. Okay, and so, right, 1 plus 0 is 1. Good, right? 0 plus 1, 1. Good. 0 plus 0 is 0, and 1 plus 1 puts a 0 in our sum column, but it also causes a 1 to be carried to the next column, right? And so if we look at this in terms of it being symbolic, then this could be a 1, and this could be a 0, which, as you recall, is what our sum was in our addition. All right? Does that make sense? But there's something you should know. This device is not quite complete. This device is known in this type of field as a half adder, right? And it's known as a half adder because what happens when you want to add more than one digit? I mean, this carries out an addition of 2 digits in a single column. But how would you add a second column to your addition? So let's stop our simulation here for a second. and go back to our slides. And let's look at full binary addition. Alright, here I have two 4-digit binary numbers, and we'll just add them together. So in the first column, 1 plus 1 is going to give 0, and we're going to have to carry to the next column. In this column, the carried 1 plus the 1 in the first row is going to add together to give us a 0, and it's also going to cause us to carry another 1 into the third column. That 1 plus the 2 zeros and the rows below it add up to 1. And then in the fourth column, we're carrying a 0, and then 1 and 1 add together is 0, and again we have a carry, and adding that to the fifth column, we have the number 10100. Okay? And so if we take this, the first row is our A column, the second row is our B column, the third row is our S column, and now we're going to add a new column called C for carry. And so let's look at the logical operations that have to happen in order to make a machine to do full binary addition. Here's our truth table. And one of the things you should notice is that now I've got these two columns are contributing to the A XOR B answer. And then I'm going to use these two, A XOR B and C, to determine the answer of A XOR B XOR C. And what that's essentially doing is saying that I'm going to take the sum of these two digits here and then add it to the digit above. Okay? And then that will give me my result that goes down here in the bottom row. Okay, so if you had A and B, right, A and B equal to 0, right, like we have in column 3, and then we would expect A XOR B to equal 0, which is the case, right? If C, the carry digit, were also 0, then the sum you would expect at the bottom of the row would be 0. If A was 0 and B was 1, and then you would expect A exclusive OR B to equal 1. And if the carry digit were 0, then 1 and 0 is going to be 1 in the bottom row, in the sum row. Likewise, if you've got A is 1 and B is 0, then you expect to get 1. And if C is also 1, then, for example, as in this row, so A is 1 and B is 0, so add those together and you get 1, like here. And then C, the carry digit, is also 1. 1 plus 1 should be 0, and you can see that it's 0 here. And then finally, if you have a 1 and a 1, A and B are both equal to 1, then you expect to get a 0 here. If you have a 1 in your carry spot, then you expect to get a 1 in your sum. So for example, if you had 1, 1, and 1 in this, so if you had 3 1s, then you would expect to have a 1 down here, and you would also, of course, get a carry. Now, so we can see that we have two XOR operations being carried out here. Basically, we've got the exclusive OR that we do on A and B, like we did in the last problem, but then we do an exclusive OR based on the result of our first exclusive OR and the carry digit. All right. Now, what we haven't accounted for is when to carry to the next place. Right. So there are two cases that require a carry, and those are when A and B equals 1, or A exclusive OR B and C equals 1. And these are those two conditions. So on the left, on the lower hand, you've got A and B equal to 1, and that column would require a carry. The other condition is when the A or B is going to be equal to 1 and C is equal to 1. And those conditions are referred to here. Now, you're going to have to come back and study this until it makes sense. But let's go ahead and I'll show you how to implement it in MMLogic. Okay, so let's, if you want to delete a wire, just click on one of the terminals and then hit the delete key. Alright, so I'm going to move these things over for a second. Okay, and so you're going to recall that in order to do this, we have our two A and B, but we need a third input now. We need a C input. And the C input is going to be for our carry, and this is going to be the carry from the last the column before, right? So we assume that this is the second, third, fourth, or subsequent column in our addition, and there's a possibility that we've got a digit that carried over from that, right? So we're going to take this digit and we're going to add it to the sum of the first two digits. And you remember that when we do a sum, we use an exclusive OR. So I'm going to add another exclusive OR here, and grab some wires, and we're going to run the result of the first addition of the two digits that we normally add, A and B, and then we're going to add them also to C. Right? And the result of that then will go into our sum column. But we still need to find out whether or not we had a reason to carry based on the addition of this one to the numbers we have so far. So I'm going to bring out another AND gate, right? And let's move it down here and get our wires, and we're going to connect the output of our this addition to the AND gate, and also we're going to connect our digit that got carried over to this AND gate as well. All right, let's maybe space this stuff out to make it a little bit easier to read. Okay. Now, if either the A and B or C plus the sum of A and B had a carry, then we need to carry to the next one. So we need an OR and a wire, and we're going to hook these two AND gates up to this OR gate. And if either one of them, these both represent the carries, if either one of them indicates that we need to carry a digit to the next column, then that will be captured in this OR gate. So OR is either this one or this one, right? And then we'll connect that to our carry, and let's test it out. Okay, so remember we've got A column, B column. If A is 1 and B is 0, then we would expect the answer to be 1. If A is 0 and B is 1, we would expect the answer to be 1. If A is 1 and B is 1, then we would get a 0, but we would also have a carry. Okay, so and now let's assume that this is the second column, and we're getting this input C as the carry from the previous column. So let's assume that we do have a digit that got carried. So from the outset, we're starting with this one plus the addition of this is always going to mean we're going to have at least 1. So if this is 1, then 1 plus 1 is going to be 0, but carry to the next column. If this one is 1, if B is 1 and the carry from the previous one is 1, then you can see this is going to be 0 in the bottom of that column of the sum, and then we're going to carry a digit to the next column. And if all three of them are on, then you can see we'll have a 1, and we'll also carry 1 to the next level. All right, so our circuit here implements addition of a column in a binary addition problem. Now, this is only a single column. What if we wanted to add multiple columns together? Or what if we wanted to do addition with multiple columns? No problem. all we need to do now is create another copy of this machine and hook up the outputs of one to the inputs of another. Alright, so I'm going to rearrange this a little bit to make it a little bit more compact, right? But and the wires will get a little bit harder to read, but they'll essentially be they are the same ones that we had before. Alright, and I'm going to move this over here, and this is our sum, and this is our carry, and now we're going to move this here, and this is the digit that got carried from the previous version, from the previous column. Alright, and now I'm going to select all this and move it up here. I'm going to copy it by hitting Control C and paste it by hitting Control V, and now I have an exact copy of this. Alright, so now I want you to think of this column as column 1. So we're going to call this one A1, and this is B1, and then we're going to think of this as S1, right, and C1, and this is going to get the value of C1, right, because we're going to carry the value that get added in column 1 to be input into column 2, right, and this is going to be column 2, so we're going to call this A2, B2, and S2, and C2. Alright, so now let's do exactly what we said. Let's get rid of this, because now instead of a switch that's independent, we want to use as the input to column 2 the output from column 1. Alright, so I'm going to delete this, and I'm going to grab my wire, and I'm going to take this output from column 1, and I'm going to hook it up to as the input in column 2 in the same places that we had C1 hooked up a second ago. Alright, so now let's go run our simulation, and let's take the addition of, let's say in the first column we've got a 1 and a 1, right? So we automatically have a carry that is carried to the second row, and in the second row, let's say we've got a 1 and a 0, right? And so now we have the binary number 1, 0, 1, 0, right? And what that is the equivalent of is saying the binary number 1, 1 plus the binary number 0, 1 is going to be 1, 0, 1, 0. Probably makes it easier if we were to draw it out. So let's open up something that we can draw this on, right? And type it in here. Let's see. So if we've got column A2 is 1, and column A1 is 1, right? Column B2 is 0, and column B1 is 1, right? And we're adding, so we'll put a little line here, right? And then if we were doing this, then we would expect in the first column we're going to have a 0, right? And it would carry, and then it would add onto the second one. So let's actually space this out over here. Right, and we'll go plus. Oops. Right. So we would expect our answer to be 1, 0, 1, right? And if we step back here for a second, 1, 0, 0, right? Because 1 and 1 makes 0, carry 1, 1 and 1 makes 0, carry 1, and that's what we have. So 1, 0, 0. And if you recall, this is just an indicator of what input goes in here. So we'll stop this. We should probably take this out just to avoid confusing ourselves and say this is C1 that gets carried over. Run the simulation again, right? 1 and 1 and 1, right? And this is exactly what we had here, right? A2 and A1 are both 1. B2 is 0. B1 is 1. And then we add those together and we get 1 in the third column, and then we get zeros in both of the first columns. So you can see here that we have multiple additions, right? And what you could do, you could take this even a step further by, right, of course, copying this and pasting it and moving it down here, and this time we're going to delete these two. Oops. Delete those two wires, delete this, and then make the input from C2 go down here to, right, this is going to be C2, and then this output, of course, is going to be S3, and this is going to be A3, and oops, B3, and this will be C3. Okay, and if we were to run this and play with it, you could see that then now we have 1, 2, 3 column addition, and you could do this as many times as you wanted. All right. So now it's your turn. You've seen the implementation of an adder. It might have been a little bit confusing this first time, but don't worry, I think you'll be able to get it, especially when you start playing with it hands-on. Have fun.